given like this. Yes. Yeah. So the PDF is given like this, and this is fairly obvious. We discussed this in class as well. Then this can be plotted, or if I try to plot the density of points in a bivariate Gaussian, the density looks like this. So there's a high concentration of points at the center, and as you move away from the center, the density decreases, and this happens exponentially. If you try to plot a 3D plot, it will be a bell. So that's where the infamous bell-shaped curve comes from. And in general, for a d-dimensional distribution, this is the probability density function. 1 upon 2 pi to the power d by 2 sigma determinant of the covariance matrix power half times this. So where we stopped last time was the point where we were discussing the covariance matrix. So the mean, I believe, is clear. That how does the mean behave? That I believe is clear, and we were talking about the covariance matrix, and the covariance matrix looks like this. Sigma equals expectation of x minus mu x times x minus mu x transpose. So the last thing that we asked was that how is this different from and when the virus interrupted us. So yeah, the answer is in the slides now, because so you can see that x minus mu x, or x, is a d times 1 matrix, and x minus mu x transpose is a 1 times d matrix. So if you look at this, this is a d times 1 times d times 1, which is a d times d matrix. And if you look at this sigma, this is a scalar essentially. So this is, yeah. So this is how the two are different. So is it okay? Any feedback will be appreciated. Guys, yeah. Thank you, Thank you, Nikhil. Back to the call. Yes. Yeah, thank you, guys. So yes, so now this is a problem actually. If we mute all the microphones, I don't know whether anything is getting across, or and if we don't mute them, then there's too much of noise. So, yeah, let's see how it works. Maybe I'll get used to it. Yeah, we have completed here. No, we stopped here at sigma. That how is the definition of sigma different? So the last thing was that sigma ij given so what we started with sigma ij is the expected value of xi minus mu xi is xj minus mu xj, which is called covariance between xi and xj. So it is how much xi and xj vary together, and there's a term defined as correlation, which is given by capital R, which is defined as the expected value of xx transpose, which essentially gives you the what is called the correlation. So the correlation and covariance are different in a way that the correlation is simply this, and the covariance is the central moment of correlation. So you know what moments and central moments are? Question. Have you guys studied moments and central moments? Yeah, excellent. So the covariance is a central moment or a central moment of correlation. Fine. Excellent. So thank you, Shri. And moreover, when so the fun thing is that the notion of uncorrelatedness or that of independence in case of Gaussian random variables is actually governed by the covariance and not the correlation. So the correlation can be zero, and if the correlation is zero, you call those variables, call those random variables as orthogonal. But if the covariance is zero only, then you call those as uncorrelated. So this is fine. And now consider the locus of a point that generates a constant PDF. So let's say we want the point for which, or we have a vector x. Now we want all the vector x for which the probability density function has a fixed value, as in here, px equals c. And in order to better visualize this, let's reduce this to a simplified case such that pxy equals c. Fine. So I can, so if I go a few slides back, pxy is this beast. So I can take the log on either side and multiply with some scalars, and what I will get is something like this k, which is another constant, not a function of x or y, but some constant which is a function of c, and possibly the variances, but that doesn't matter right now. So the question is, what is this? So I have an equation in terms of x and y that so x equal, so this equation, yeah, I don't have a pen here. So this equation, what does it say? Or what is this equation? I'm looking at the chat box. Or someone can potentially unmute and tell me what this is. Yes. So there is an equation on the screen. Yeah, so now I'll force people to view the slide that I am viewing. So yes, all of you can see the slide, right? So the question is that this equation for a given the point, or the equation for all the points where the PDF is constant, what does that equation look like? Or what does that equation remind you of? Yeah, exactly. This is an ellipse. So a generalized ellipse that actually a rotated ellipse, because of this. So this ellipse, the focus is not at the origin. Sorry, it's not centered at the origin. I'm sorry about the focus. Yeah, this is rotated, and in general, try to imagine for a d-dimensional random variable. Try to imagine this ellipse in d dimensions. So that's how a correlated Gaussian random variable in d dimensions will look like. So now you get a strange focus. Now let's simplify things a bit and say that we have x and y as related, which means this rho is 0, the correlation coefficient is 0. So you get or x and y is orthogonal, you can say as well. So for x and y equals 0, so you get this beast. I've just chopped off the last part. So it's still an ellipse, but how does it change? That is the question. Yeah. It is an ellipse. I'll show you an ellipse in the next slide. But the question is, how does this ellipse change? Yes, exactly. The foci are now along the axis, and this is a lot more well-behaved ellipse as compared to the one we had earlier. Now let's go a step further. If sigma x square is equal to sigma y square, we get a circle. So, and in general, for d dimensions, we'll get a sphere, right? So if the variables are uncorrelated, you get the foci along the axis, and if the variances are all equal, or the covariance matrix now is a multiple of the identity matrix, then you get a circle in 2 dimensions and a sphere in d dimensions. So essentially, any Gaussian random variable, if you can reduce it to you can reduce the covariance matrix to an identity matrix or a multiple of the identity matrix, you can think of the distribution as the point, or the points from the distribution as distributed along a d-dimensional sphere, or at least a d-dimensional ellipse. So the question now is that how do we go from beast like this, a sphere in d dimensions that is overly misbehaved, to a nice spherical distribution of points? So, any guesses? Yeah. So you understand the point? First of all, if you want me to repeat the point, I'll repeat it. Yeah. So, okay, Harsha, can you unmute and talk? That will be easier for everyone.
Yes, sir.
Yeah, Harsha. Hi. So, tell me, where exactly is so till what point did you understand?
Sir, when sigma x square is equal to sigma y square, it turns into a circle, and then but in d dimensions, I have not understood where I'm going to d dimensions, right?
Okay,
Like,
so you understand that. So this is in 2 dimensions, right?
hmm. Yes,
So
sir.
in 2 dimensions, it is a circle, fine. So if I try to write it in d dimensions, the equation will be essentially a summation of x1 minus mu1 square, x1 minus mu1 whole square plus x2 minus mu2 whole square plus x3 minus mu3 whole square, and so on.
Yeah. Hmm.
So that will be a hypersphere in d dimensions.
Oh, okay, sir.
Okay, so
Yeah.
now the point is that it's easier to manage points on a hypersphere than on an hyperellipse.
Hmm.
Or
Ah,
the question that I would be asking is that I have a correlated random variable, random vector whose entries are correlated. So, but I want that the entries of this should become uncorrelated, so they turn into a sphere. Or rather, what we can say is the sphericity of, so if you
So for
consider it as
them
a
to be
sphere, then
unrelated,
yeah,
so for
yeah,
them to be
we are
unrelated,
coming to
it has
that.
to be a sphere.
Yeah, for them to be uncorrelated, it has to be a sphere. Or you can say that the more the sphericity of the thing,
The more the
the
uncorrelated.
more the uncorrelatedness, or the more the sphericity, the less the correlation.
Yeah.
Okay, and
Okay.
we'll eventually come. Okay, so we'll eventually come to the point where we'll talk about why we don't want correlation. Possibly, if this continues in 3 or 4 more lectures, we'll come to the point where we'll talk about why we don't want more, we don't want correlation. But in general, we don't want correlation among the features. So we want that to go from that ellipse to this sphere, or we want to increase
So
the
that each and
sphericity.
yeah. So that each and every future that we want to expect can be totally different from each other.
Exactly, exactly.
Yeah.
So because we want each and every feature to be independent of each other. So say you want the height and the weight. The height and the weight are highly correlated. You want
Yes.
height and weight as features for something, but generally a tall person will have more weight for same build. So
Yeah.
if you want to check the fitness, height and weight separately aren't two relevant features, but the BMI, which is weight divided by the square of height, is a nice feature. So instead of two correlated features, you can check the fitness of a subject using just one feature. That's why you would want uncorrelatedness. We'll come to this possibly next chapter. Right now,
Okay.
I'll say that we want uncorrelatedness. And now, if that answers your question, I'll go back to my monologue. Excellent. So you can mute again. Yeah, thank you. So now the question is, how do we go from A to B to C? That is, how do we go from a rotated ellipse to an ellipse to a sphere? So we know that this covariance matrix is symmetric. So you have non-symmetric matrices, right? So you know symmetric matrices, and you know diagonalization. So all symmetric matrices can be represented in this form: sigma equals q lambda q transpose, where q are the eigenvectors of q is a matrix containing the eigenvectors of sigma, lambda is a diagonal matrix containing the eigenvalues, and q transposes. So, and q is such that q transpose equals q transpose q equals the identity. This is called a unitary matrix or an orthonormal matrix. Yeah, this is called an orthonormal matrix. Unitary is in terms of for complex matrices. So this is an orthonormal matrix. So far, so good. If you have problems with diagonalization, now is a good time to ask. So everyone is okay with diagonalization. I believe that. Okay, I'll wait for 10 seconds. If anyone has problems with diagonalization, write it now. Excellent. So all of you are comfortable with diagonalization. All of you are comfortable with this form. So let's say I define y equals q transpose x. When I define y equals q transpose x, the expected value or the mean will now move to Q transpose mu X, which is on the expected lines, and the covariance matrix will now look like this. So I believe everyone is able to see this. So the covariance matrix looks like this. I do what happened? Yes. So this inner part turns to sigma, which in turn is Q lambda Q transpose. So I can write Q transpose Q lambda times QQ transpose, which is lambda. So this allows me to go from a rotated ellipse to a conventional ellipse. Fine. So now I have what I have done is I have diagonalized the covariance matrix, or the covariance matrix of this Y will be diagonal, which means that the cross correlation terms are all zero. So I get uncorrelated features. Now the next step is, if I define Y equals lambda inverse, lambda to the minus half Q transpose X, then mu Y turns into this, and the covariance matrix turns into an identity matrix. I get a sphere, or each point with a constant probability for this new random variable Y or new random vector Y will lie on a sphere. So this is how I introduce sphericity into random variables. We'll revisit this whenever we discuss principal component analysis. So now this done, we have covered Gaussian random variables. Now we come back to the binary hypothesis testing problem that we were discussing earlier. So just give me a second. So what I'll do is yes, sorry about Thor. Yeah. So you see this, right? So now if I remove this line for a minute, you consider a binary case where you have we have talked about the radar in the class. So in the radar problem, there are two cases. One, you see nothing but noise. Two, you see some data plus the noise. So the yellow cluster is nothing but the noise, and the purple cluster is data plus noise. And you want to know whether a point that you encounter comes from the yellow cluster or it comes from the purple cluster. So now, how do I find that out? So the first thing that you would see is that within the clusters, there's no, or between the clusters, there's no clear demarcation. There is some yellow in the purple and there is some purple in the yellow. So obviously, you cannot say that there's a direct one-to-one, or there's a direct rule that you could follow, or there's a clean line that you can draw, like I had drawn earlier. So there is no clean line. So this is one line that you can use, but you can move this line anywhere. So there is some yellow over here, or there is some purple over here. Now you want to know that, okay, I want a low probability of misdetection, or I I want a low probability of missing the purples. So what I'll do is I'll move this line here. So again, I'll repeat. I draw a line and everything to the left of that line is classified as yellow and everything to the right of that line is classified as purple. So I move this line. So if I don't want to miss any purple, I'll move this line here. And so now what I do is I include a lot of yellow in the purple. But if I say that, okay, I don't want to misclassify any yellow as purple, then possibly I have to have the line over here so that there's no purple classified as yellow. So again, I miss out on purples now. And then there's the minimum error criterion such that the line sits somewhere over here, where you can say that, okay, there is a trade-off between yellow and purple. So you get this? Have to move to yes. Yeah. So since no one is responding, I believe that you get this. Now let's move to MATLAB and say that so this was the original figure. I close this and what I'll do is I'll change noise power. Now you see that in this case, I have actually increased the power of the noise. So the yellow and the blue and the orange. So blue is the case where there is something else present and the orange is the case where there is nothing else present. And here it has become harder to draw that line. So the question that we want to ask is how to draw this line between yellow and between blue and orange so that we do not mistake one for the other or the probability of error is minimized. So I'll move back to the call. Yes. So that was the presentation. I didn't realize that it will take just 35 or I've made just 35 minutes of presentation. So possibly with time we'll improve. So now I am open for questions. Yeah. So you can unmute and talk. And Friday, I'll prepare something longer. Hopefully.
Sir,
Yeah, Harshit.
sir,
Yeah, Harshit,
to convert any ellipse into is diagonalized, like to convert an ellipse into like a circle,
Yeah.
all we have to do is diagonalization, right, sir? Like
Yes. Diagonalize and so the point is that here what you are doing is you are multiplying each feature vector with the with that eigenvector eigenmatrix. So you are not essentially, if I'll go back to the presentation, just a second. I'll go back to the presentation. So yes, so that's the key difference, that you are not actually diagonalizing. What we're doing is that you know this Q and so from the covariance matrix you can calculate Q and Q transpose, and now each time you want to change the answer, you'll multiply each x with this Q transpose. So each random vector that you generate will be multiplied with Q transpose. So that's not exactly diagonalization.
Oh.
You see the difference. Yes.
So, but we wouldn't be getting the same dimension matrix like how we were getting in the past, like
No, you'll be getting the same
like
dimensional matrix.
like
So this
like for
Q
that
is D
it
times
must
D.
be a n into n matrix, right?
Yeah, in this case D, because we are still following the book and considering a D dimensional matrix. So this Q will be a D times D matrix. Lambda will be a D times D matrix, assuming that all the eigenvalues are non-zero. So and sigma is also a D times D matrix. So given that X is a D times one vector, Y will also be a D times one vector.
Okay.
Okay. Yes. Great. So next time we'll actually consider how to partition. So there are something called discriminant functions that I thought that I would be able to cover today, but I went faster. So next time we'll cover discriminant functions. Anything else? Great. So the recording will be available with me possibly in a couple of hours. I'll upload that to YouTube and share the link with you guys, and all those who couldn't attend can look at it. Sound good? Okay. I take it as a yes. Okay, guys. Thank you then. Nice to you.